Hello and welcome to this video where I'll explain how to solve any ODE in this form using the method of variation of parameters. And so I kind of have everything that you need to know already on the screen right now. It'll just maybe take a little bit of memorization to kind of get this down like that. In the meantime, take a screenshot, whatever. I'll be going over each individual piece of information as we go into it, as we run into it in the example. Something that maybe you haven't run into before is the Wronskian right here, and it's just a definition. The Wronskian of y1, y2 is just the determinant of y1, y2, and then those are over their derivatives. I mean, we'll get into what that actually looks like, but the only reason that we need to know what a Wronskian is here is because the actual integrals that are going to give us our particular solution, or part of it, include that Wronskian. Okay, but let's go ahead and get into an example here. Okay, here we are, and so as you can see, g of t in this case, g of t is what I call what is on the right side of the equal sign. G of t here is something that could never work with the undetermined coefficients method. So I chose this example to start because this is something that you can only really solve with the variation of parameters method. What you may know, the undetermined coefficients method does not work for any type of quotient like this. But let's just go ahead and start by finding the homogeneous solution. Any type of ODE in this form, that's how you always start. So y double prime minus 2y prime plus y equals 0, right? This is the homogeneous part. Let's write that characteristic equation, r squared minus 2r plus r equals 0. Now we just have to solve for r. Luckily, this is nice and factorable. Two numbers that add to -2 and multiply to 1 is just going to be a r minus 1 and an r minus 1, right? And that's going to go ahead and equal 0. Okay, and that just gives us a singular root of r equals 1, right? And so now we can just go ahead and write the homogeneous part of this equation down already. This is a double root situation, so that's going to be in the form c1e to the rt. So in this case, r is 1, so it's going to be t. Now, since this is a double root situation, we need to multiply by a t right here, and then we just maintain the e to the t. Okay, but that's probably something that you already knew. So let's go ahead and get into variation of parameters here. This is just very necessary for the method because if you remember, the homogeneous part is in the form c1y1 plus c2y2. And we need both of these guys right here to find the particular solution. So in this case, this guy right here is going to be y1, and this whole guy right here is going to be y2. So I think what makes the most sense now is to go ahead and find the Wronskian. So as we said up above, the Wronskian of y1 and y2 is going to be the determinant of y1, y2 over their respective derivatives. Okay, so what does this look like? Well, what's y1? Well, y1 is just e to the t as I have marked. y2 is just t e to the t as I have marked. So what's the derivative of e to the t? Well, that's just a nice e to the t. What's the derivative of t e to the t? That's going to be a product rule situation, but that's going to be a nice and simple one. So I'll let this guy be u, this guy be v. So u prime v is just going to be e to the t, and then we add u v prime, which is just going to be a t e to the t like so. Okay, now we can go ahead and evaluate this determinant. So if you don't know how to go ahead and solve a determinant, you're going to multiply these two guys, and then you're going to subtract those from the product of these two guys. Okay, so let's go ahead and do that. So this is the same thing as e to the t times e to the t plus t e to the t, and then we're going to subtract the blue circled terms, e to the t, and that's going to be multiplied by a t e to the t like this. So this will give us our Wronskian. So let's see, well actually I see terms that cancel immediately. So this is a negative e to the t times t e to the t, and if we multiply this e to the t right here, we would have the same term but positive. So actually the only term here is going to be this guy, this product, and that's going to be e to the 2t. Okay, so we have the Wronskian, we have the homogeneous solution, and now we need to go ahead and find u1 and u2, because if you remember, the particular solution is in the form u1 y1 plus u2 y2. Another reason why we need to know our y1 and y2 before we go ahead and start this method. Okay, if you remember the formula up above, u1 equals the negative integral of y2 times g of t. Then you just have a dt, and that's going to be over the Wronskian of y1 and y2. Okay, so we can actually go ahead and evaluate this integral with everything that we know. So what's y2? Well, we marked y2 up above to be te to the t, if you remember. So let's fill that in. This is still the negative integral. Now we know there's going to be a te to the t here. So what about g of t, right? Well, g of t is actually going to be this function up above right here. Because if you remember, we call this function on the right-hand side of the equation g of t. So that's going to be a e to the t over t squared plus 1. Okay, e to the t plus t squared plus 1. Now we're going to still have that dt. And what did we say the Wronskian was? Well, we said it was e to the 2t, right? Okay, so this integral looks nasty, but actually a lot cancels. This is the same thing as the negative integral, and well, what happens here, right? We have an e to the 2t right here, but if we were to multiply this e to the t to this guy, we would have an e to the 2t in the numerator as well. So actually, this is going to be a e to the 2t over e to the 2t, which is just going to be 1. So simplifying this integral, this is actually the integral of t over t squared plus 1 dt. Okay, now this integral is not so bad either. We can actually use a quick u substitution here. So if we said that u equaled t squared plus 1, and therefore du would equal 2t dt, then this integral becomes no problem. So this is the same thing as the negative integral of t over u. Now what did we say dt was? Well, dt is going to be du over 2t. So du over 2t. So this is the same thing as negative 1/2 times the integral of 1 over u du. Okay, so what is the integral of that? Well, that's just one that we know. That's just a natural log of u. And so what did we say u was? Well, we said it was t squared plus 1, like so. Okay, so this is actually going to be our nice u1, but now we need to do the same thing for u2. So let's go ahead and find u2. This is defined as the integral from y1 times g of t dt multiplied, or rather divided by the Wronskian y1, y2. Okay, so what is y1? Well, y1 is all the way up top, right? We said y1 was e to the t, so we can fill that out. Okay, so e to the t, and then nothing changed about g of t. That's still going to be just e to the t over t squared plus 1. dt remains, and then this is still over the same Wronskian of e to the 2t. So actually the same exact cancellation happens here. Every e kind of disappears, except now there's no t on top. So this is going to be the integral of 1 over t squared plus 1 dt. And actually this is one of the integrals that they maybe made you memorize in calculus 2. This is the same thing, or this is the arctangent of t. Okay, and that's going to be our u2. And finally, we can kind of put everything that we know together. The particular solution, if you remember, is just a u1 y1 plus a u2 y2. So what's u1? We found that up above. u1 is negative 1/2 natural log of t squared plus 1, and that's going to be multiplied by a y1, which is e to the t. So we have a negative e to the t over 2 times the natural log of t squared plus 1, like that. That's going to be this piece taken care of. Now we need to add a u2 times y2. So what's y2? Well, earlier in the problem we said y2 was t e to the t, and we just said that u2 was the arctangent of t. Okay, so we have our particular solution, and if you remember, the first step of this problem was getting the homogeneous solution. And the final answer is going to be the summation of these two pieces of the problem. Okay, so what was our homogeneous solution? Well, our homogeneous solution is all the way up here, and that is going to be a c1 e to the t plus c2 t e to the t. Okay, c1 e to the t plus c2 e, or rather c2 t e to the t. Now we just go ahead and add our particular solution, which is right up above. Okay, this is a minus e to the t over 2 times the natural log of t squared plus 1. And then we get to add a t e to the t times the arctangent of t. Okay, and so that is our final y of t. And so actually, this was not too bad to find, right? And it's a really powerful tool to know this method, because you would never be able to solve for this particular solution using the undetermined coefficients method. It's just not possible. And so the variation of parameters method kind of trades the algebra from undetermined coefficients for a couple of integrals. And because of that trade, you get to deal with a lot more different kinds of that g of t or g of x, whatever variable is on the right-hand side. Okay, so let's go ahead and get into another example. Here we are with another example, and I think this one's pretty cool because variation of parameters must be pretty powerful if it can solve an ODE that looks this complicated, right? A sine of e to the x, well, you don't see that every day. But it starts just like every other ODE of this form, and we want to find that homogeneous part of the solution. So that's when the right-hand side is equal to 0, right? And we can just go ahead and write our characteristic equation out. R squared plus 3r plus 2 equals 0. So this is nice and factorable, right? Two numbers that add to 3 but multiply to 2. And so that's just going to be a 2 and 1. So r plus 1, r plus 2 equals 0. This gives us two roots, r1 equals -1, and r2, which equals -2. Okay, so we can write out our nice homogeneous solution now. This is just going to be a c1 e to the -x plus a c2 e to the -2x. And if you remember, the homogeneous part of the solution is in the form c1 y1 plus c2 y2. So we can go ahead and just say this is y1 and this is y2. And that's going to help us finding the Wronskian. So the Wronskian of y1 and y2 is going to be them at the top, right? E to the -x, e to the -2x, and then their derivatives right below. What's the derivative of e to the -x? Well, that's going to be a -e to the -x. And then a derivative of e to the -2x is a -2e to the -2x. And this is a determinant, so we want to multiply these guys and then subtract these guys. And so what does that become? We have a e to the -x times -2e to the -2x. Then we have a minus e to the -2x, and then multiplied by a -e to the -x, like so. Okay, so let's just go ahead and multiply this out. This gives us a -2e to the -3x plus a e to the -3x. Okay, so this actually equals -e to the -3x, like so. And so that's going to be our nice Wronskian. And once we have the Wronskian, we can go ahead and solve for u1, u2, which are the components of the particular solution. So if you remember, u1 equals the negative integral of y2 g of x dx over the Wronskian. So what's y2? Well, we defined it right up above, right? It's e to the -2x. So this is the negative integral e to the -2x. What do we say g of x was? Well, g of x is the right-hand side of the original ODE, which is going to be a sine of e to the x. So this is a sine of e to the x, like that. This is a dx, and then we get to divide by that Wronskian, which we said was a -e to the -3x. So now all we have to do is evaluate this integral. And first of all, we have a e to the -2x in the numerator and a e to the -3x in the denominator. And so there's going to be some sort of a cancellation here. So this negative is going to cancel with this negative first of all. We're going to be left with the integral of e to the -2x times e to the 3x, right? Because the sign on the exponent flips if you bring something from the denominator to the numerator. And this is still times sine of e to the x dx. Now the reason I did this here is because if you're multiplying two numbers that have the same base but different exponents, well, you can go ahead and add those exponents. So here it's pretty easy to see that this is the integral of e to the -2x plus 3x, which is just a nice e to the x, times a sine of e to the x dx. So now all we got to do is evaluate this integral. And actually, with a nice u substitution, this integral is not half bad. Let's say u equals e to the x, and therefore du equals e to the x dx. So this becomes the integral of e to the x times sine of e to the x. Now we want to replace dx with du, so that's going to be a du over e to the x. And actually this u substitution was great because these e to the x's cancel. And if you remember, we said e to the x itself was already u. So this integral in its most simple form is sine of u du. All right, nice. What's the integral of sine? Well, that's going to be a negative cosine of u. And what was u? Well, that was an e to the x. So the answer to this integral is a negative cosine of e to the x. And that's going to be our answer for u1. Okay, so now all we need is u2. And u2 follows a similar formula, right? Here, I'll get a kind of everything blank for us here. We know that u2 is equal to the integral of y1 g of x dx. And that's going to be still over the Wronskian. We defined y1 up above. y1 is going to be right here, just an e to the negative x. And g of x is still that sine of e to the x. So this is the integral of e to the negative x times sine of e to the x times dx all over the Wronskian, which if you remember is a negative e to the negative 3x. Okay, so there's some simplifying here for sure, right? Now we're going to just have a integral, and don't forget the negative, we have a integral of e to the x times e to the 3x. So we add those exponents, what's negative x plus 3x, that's just going to be a 2x, right? So we have an e to the 2x times sine of e to the x times dx. And so how do we evaluate this integral? Well, actually, you can use a very similar, actually the exact same u substitution this time around as we did in u1. Let's say du then equals e to the x dx. Okay, so we can plug in what we know. This integral then becomes negative integral. Now, what's e to the 2x in terms of u? Just u squared. So then we have a sine of u. And then we want to replace dx with a du, right? So dx is going to equal du over e to the x. But we said e to the x was u. So this is actually going to be a du over u. So one u is going to cancel, and we'll be left with the negative integral of u times sine of u du. Okay, so this is just going to be a integration by parts question, basically. And so if you remember the formula for integration by parts, the integral of gamma dv is equal to gamma v minus the integral of v d gamma, like so. So let's just go ahead and find our gamma and v. So in our case, gamma is going to equal u. Our d gamma is going to be that derivative. That's just going to be, well, a du. Okay. So then we're going to have a dv. dv in our case is going to be sine of u du. What's the integral of sine of u du? That's going to be a negative cosine of u. Okay, now we have everything we need, and so we can plug this back in. This is then equal to negative because that negative was already out front. And then we have a gamma v, so we have a negative u cosine of u minus the integral of v d gamma. So this is going to be a negative cosine of u. And then d gamma is just a du. So actually, this negative will cancel with this negative, and we'll just be left with a plus here, and then we can go ahead and erase this negative. Okay, so we can go ahead and solve this integral. Negative times negative u cosine of u. And then we have, what's the integral of cosine? That's just a sine of u. Distributing out that negative, we are left with a u cosine of u minus a sine of u. And what do we say u was? We said it was e to the x. So finally, this equals e to the x times cosine of e to the x minus a sine of e to the x, like so. And this is our final u2. So now we have everything we need for our particular solution. If you remember, the particular solution is in the form u1 y1 plus u2 y2. So what is u1 and what is y1? Well, we said u1 was a negative cosine of e to the x, and we said y1 was a e to the negative x, if you remember. And that's because we have a u1 right here, negative cosine of e to the x, and we have y1 right here, e to the negative x. Now we just need to go ahead and find u2 and y2. So u2 we just found, that's going to be a nice e to the x cosine of e to the x minus sine of e to the x, like so. And then we need to multiply that by y2. And y2, if you remember, was negative, or e to the negative 2x, like this. So I'm sure there's some simplifying to be done here, so let's go ahead and do that. We have a negative e to the negative x times cosine of e to the x. Now we have a plus e to the negative x times cosine of e to the x. Okay, that's good news. It looks like those are going to cancel. Then we have a minus e to the negative 2x times sine of e to the x. So yeah, these are going to cancel, and then we're just going to be left with a negative e to the negative 2x sine of e to the x as our particular solution here. And our final solution is then just going to be the summation of our homogeneous part and our particular part, right? So we said that our homogeneous part was c1 e to the negative x plus c2 e to the negative 2x, and we just said our particular part was minus e to the negative 2x times sine of e to the x, like so. Okay, and that's going to do it for our final solution for this problem. I thought this one was pretty cool because of that sine of e to the x, right? And somehow we were still able to solve it with relatively little trouble. Okay, let's go ahead and get into one more example here. All right, here we are with our final example of the day. And so this one's going to start just like how every other ODE of this form does, and that's with the homogeneous part of the equation. So that's when the right-hand side equals 0, right? So y double prime minus 2y prime plus y equals 0. We follow that up with the characteristic equation, which looks like r squared minus 2r plus 1 equals 0. So we just need to solve for r here. And so this is nice and factorable. We're going to have a r minus 1 and a r minus 1, right? Because negative 1 times negative 1 is 1, and negative 1 plus negative 1 is negative 2. So this is nice and factorable. Okay, that means we have one root, and that's just 1. So what does this tell us about the homogeneous part of the equation? Well, that it's c1 e to the x plus c2 x e to the x, like so. Okay, now we can go ahead and do the variation of parameters method, basically, and that starts with the Wronskian. So the Wronskian of y1 and y2, where y1 and y2 are these guys respectively, is going to look like the determinant of y1 e to the x, y2 x e to the x, and then their respective derivatives. So the derivative of e to the x is e to the x. The derivative of x e to the x with the product rule is just going to be an e to the x plus x e to the x. Okay. Let's go ahead and evaluate this determinant. And so we're going to have a e to the x times an e to the x plus x e to the x minus a e to the x times x e to the x, like so. So if you notice, this term is going to multiply here and give us a x e to the 2x, and this term is going to multiply here and give us a negative x e to the negative 2x. So those terms are going to cancel. We're just going to be left with this term right here, which is just a simply e to the 2x. Okay, we have the Wronskian, we have y1, y2, so we can go ahead and find u1 and u2. Well, u1 is just going to be the negative integral of y2 g of x dx over the Wronskian, okay? Okay, we know what these values actually are, so we can kind of plug them into here. y2, we said up above, was going to be x e to the x, right? So that's just going to start with an x e to the x. What's g of x? Well, it's this guy right here, so that's an e to the 2x. So we have an e to the 2x here, and so we need to divide by the Wronskian. What's the Wronskian? Well, that's also e to the 2x, and then we need to take that integral with respect to x. So these guys are going to cancel, and we're going to be left with a negative integral of x e to the x dx. And this is going to be a integration by parts. So here u equals x, du equals du, and now instead of gamma, I'm calling it u because this is a more familiar version. I only used gamma in the last problem because we had a u substitution already. So what's dv? Well, that's going to be an e to the x dx, and so then a v is just going to be e to the x. So this whole integral becomes the negative integral of, well, uv, so x e to the x, minus the integral of v du. So that's just going to be an e to the x times du, like so. So what does this actually end up as? A negative x e to the x, and then a plus e to the x here. Okay, so now we can go ahead and solve for u2 as we just solved for u1. Okay, u2 is a similar formula, right? Except this time it's y1 g of x dx over the Wronskian. So what's y1? Well, y1 is just an e to the x, g of x is an e to the 2x, and then this is also an e to the 2x, the Wronskian. Let's take that integral. This is the same thing as the integral of e to the x dx, as these guys cancel, which, as we all know, is e to the x. Okay, so u2 was a lot easier here, right? And we can sort of put together the particular solution now. This is going to be u1 times y1. So we have u1 negative x e to the x, or just regular x, plus e to the x. And then what was y1? Well, y1 is e to the x. So we have a e to the x here. And then we have a plus u2 times y2. Well, u2 we just said was e to the x. What was y2? Well, y2 is up top. We said that's x e to the x. Now, I'm sure there's going to be some cancellation here. So what do we see? Well, I see an e to the x times an x e to the x, and then I see a negative x e to the x times e to the x. So these guys are going to cancel, right? This is going to actually be a just e to the x times e to the x, this term right here, as these cancel. What is that? Well, that's the same thing as e to the 2x, like so. Okay, so we have our particular solution, we have our homogeneous solution. All that's left to do is combine them into one final solution in this form. Okay, so what's y? Well, what was the homogeneous solution? That was going to be c1 e to the x plus c2 x e to the x. What was our particular solution? Well, we just found it to be e to the 2x, like that. And so that's going to be our final solution here. Okay, so this was just a showcase of the variation of parameters method. So let me know if you guys have any questions or want me to go over anything else specifically. All right, thank you.